Okay, guys, so this is my walkthrough of the 2023 chemistry exam. Now, just a note, this is from the previous study design. So there will be a lot of food chemistry stuff there that isn't entirely relevant, but I think it's still good to go through. One, just because, it might come back in the future. Anyway, which one of the following represents the reaction of glucose in human cells? So it would be exothermic because it's releasing energy, and most likely be respiration. Um, Hydrolysis, not really. The reaction itself is respiration. Okay, we respire. It's aerobic respiration. Hydrolysis, even though we are breaking down the glucose molecule into its smaller constituent molecules, I wouldn't go as far as saying it's hydrolysis. Okay, hydrolysis is when we're physically, using water to break it down. And in this situation, I guess it's literally producing water. Which one of the following statements is correct? So fuel cells and galvanic cells produce heat. That is correct. Okay. So although there is a direct conversion of chemical to electrical energy, it isn't 100% conversion. Okay. We can pretty much never ever um, guarantee that there's going to be 100% conversion. There'll be, even if I were to take the brightest pathway, there would still be at least 1% of energy that's converted into heat energy, right? So A is looking pretty good. Fuel cells have inert electrodes, whereas galvanic cells do not. So galvanic cells can have inert electrodes, especially when you're looking at half cells. So, especially when you're looking at half cells that only have that both have ions, so like for example, tin 4 plus and tin 2 plus. The best electrode to use in this situation would be a platinum or a carbon electrode. So yes, galvanic cells do use inert electrodes. Fuel cells have porous electrodes, whereas galvanic cells do not. Generally speaking, that also tends to be true. However, it's not like galvanic cells can't have porous electrodes, right? Like, what's stopping galvanic cells from having porous electrodes from increasing the reaction rate, right? From increasing the surface area to volume ratio and therefore increasing the reaction rate. Fuel cells and galvanic cells operate when electrons flow through the electrolyte. So electrons never flow through the electrolyte. The electrolyte is the internal circuit where ions flow through. So C, I would say like the second best answer would be C, because generally speaking, galvanic cells don't have porous electrodes. However, A is probably our clearest best answer. Um, so what is the order of melting points from highest to lowest for these three molecules? So yeah, don't get caught up in the fatty acids and all that sort of stuff. What we have here, X, Y, Z are triglycerides, each composed of three different fatty acids. And the best thing to do, the only difference between these three triglycerides is the number of double bonds, right? And what you guys have to remember is that whenever we introduce a double bond into a molecule, we're introducing a kink into the fatty acid. And what that kink does to that structure is it actually prevents the fatty acids from packing as tightly, and therefore it actually reduces its melting point. So, in a simple way, the more carbon to carbon double bonds we have, the less the melting point would be. So, Y has no double bonds and therefore is a saturated molecule and therefore would have the highest intermolecular forces. This only has one double bond. This has three, so it'd be YXZ, which is A. Cool. A cell can be considered a secondary cell if it has a continuous supply of reactant, so that is a fuel cell. It can operate at different temperatures. Okay. The polarity of the electrodes remain unchanged. That is true. It can operate as both a galvanic and an electrolytic cell. Okay, so the polarity of the electrodes remain unchanged. That is actually not true, right? Because basically what happens is the anode. Okay, initially during discharge is negative, but then but during recharge it becomes a positive. What I was thinking when they said the polarity of the electrodes, I was thinking about like how secondary cells, the negative and the positive, they stay in the same position, but the reactions happening there change, right? But yeah, this is saying electrodes, so electrons meaning anode and cathode, which are obviously different. It can operate at different temperatures. Just because it operates at different temperatures doesn't mean that it'd be a secondary cell. Okay, so I'd say D. Which one of the following statements are correct? So coenzymes assist enzymes to catalyze a reaction. That is true. They literally are called coenzymes. So co-workers help other workers to catalyze to do the job, right? So coenzymes, they're just co-workers, right? Coenzymes bind loosely to the active site of an enzyme. Coenzymes act as carriers in the transfer of electrons and atoms. Yeah, like they do bind loosely to the active site of an enzyme because they kind of fall off after the reaction is actually finished. So um, this talks about its structural component. This talks about its chemical component. So the two reasons as to why coenzymes are great at catalyzing reactions, and you actually can't, the reaction actually can't go ahead without the coenzymes, is because they actually help augment the site of the enzyme, the active site of the enzyme. So the coenzymes basically ensure that um, the overall active site of the enzyme is more complementary to the substrate, and they also act as carriers, intermediate carriers of electrons and H plus ions. So as 1, 2, 3 is correct. Consider the following statements: HPLC is a qualitative process. HPLC is a constant. Triplets give information about the which one of the following statements apply to HPLC? So, um, well, triplets give information about molecule structure. That is talking about NMR. So that's talking about splitting patterns. HPLC can be a qualitative process because we can look at retention. We can look at how polar a molecule is, looking at retention time. It's also a quantitative process because we can basically find out the concentration of certain things such as caffeine, for example, in coffee, things like that. Because we create the calibration curve, right? So there's a quantitative, but there's also a qualitative aspect to it. So 1 and 2. Production of biofuels does not damage the environment. Look, generally speaking, um, from if you're sort of very, early into your studying of chemistry, you might believe that is true. However, um, you don't know that for sure, right? There's a lot of different factors involved in producing biofuels. For example, even like when we're looking at like, you know, fermenting glucose into bioethanol, there's actually a lot of steps that go into that, right? So we don't know what's, happening to the environment. There's a lot of industrial processes that happen into breaking down the sugar cane, right? Which could produce CO2, which could damage the environment. We are also growing crops, right? So a lot of these biofuels come from crops, and we're actually cutting down these crops. So we're actually reducing the amount of arable land that we have that we should be dedicating towards food, but towards fuels. So, I would not agree with this. Combustion of both biofuels and fossil fuels generates greenhouse gases. Yes, that is true. So, biofuels, they operate in the same exact way as fossil fuels. And a great example of that is bioethanol and ethanol. So, bioethanol is a biofuel, and ethanol is a fossil fuel. However, when we burn them both, they both produce CO2 and H2O, right? So they're both producing greenhouse gases. The only differences between bioethanol and ethanol, so the structures are the same. The only differences between the two is where they're coming from. So that's all good. Biofuels and fossil fuels are both renewable as they're produced from plants. So fossil fuels are non-renewable, right? They could be produced from plant matter. I'm not saying that they're not, but they're not renewable. So I would say only two is correct. Um, So what is the equilibrium constant? So basically what's happened to this? Oh, that's super easy. All that's happened is whenever we double the reaction for equilibrium, we have to square this. So 4.1 squared is most likely going to be 16.8. Now the reason why these two exist, so the difference in units, this would be basically be 4 over 6 times 2. Is that right? No. So it'd be okay, so think about it in terms of, sorry, I don't know why. So we think of the concentration as x, so it's x to the power of 4 over x to the power of 2 times x to the power of 6. So why am I overthinking this? Am I doing something wrong here? X to the power of 6, x to the power of 2. So therefore, it'd be 1 over x4. So it'd be d. Okay, so it'd be x minus 4. So m minus 4. Coal seam gas and petroleum gas, they're both mixtures. Yeah, so coal seam gas, you can't really, like, yeah, you can't really you guarantee that coal seam gas is going to be pure methane or whatever it is. So coal seam gas is basically the gas that's found whenever we're fracking for coal, whenever we're mining for coal. And it tends to be like, a pretty high percentage of methane alongside carbon dioxide, right? So that's a mixture. And then petroleum gas, obviously, it's produced via the distillation of crude oil. So that'll still be a mixture of, different types of alkanes and things like that. Coal seam gas and petroleum gas both combust to produce carbon dioxide. Yeah, so any fuel that we're oxidizing that's carbon based, if you combust them, you're fully oxidizing them. And so then you're going to produce carbon dioxide, most likely. And then they're both fossil fuels, yes. So coal seam gas it comes from coal, and then petroleum gas comes from like crude oil. So they're both fossil fuels, right? So yeah, I'd say that's pretty obvious. Which one of the following always corresponds to the increase in the yield of chemical reaction and increase in the value of the equilibrium expression? So if you increase the value of the equilibrium expression, then the products are basically going up and our reactants are going down. So I'm pretty happy with that. So that's good. An increase in the concentration of the reactants, which one of the following always corresponds to an increase? An increase in the concentration of the reactants. It does. An increase in the pressure. That's kind of dependent on um that's dependent on the mole ratio on the between the reactants and the products, you know. And decrease in the activation energy. So that would affect rate of the reaction, not yield of a chemical reaction. An increase in the value of the equilibrium expression. I'm kind of happy with that because I'm really, because it's saying always. And the equilibrium expression is literally, right, an expression of how much, like, what is the proportion of products to the reactants. And if there's an increase in that, then it would almost certainly indicate that there's more products relative to the reactants. Now, the reason why I'm not happy with the increase in the concentration of the reactants is, even if we do increase the concentration of the reactants, like say, for example, we have X plus Y equals to Z, we increase Y, therefore LCP will say, let's decrease Y, and it would favor the forward reaction. Um, but perhaps the point here is that it's only going to be a partial response, and reactants are going to be the reactants are going to increase much more proportional to the products, right? Because it's only a partial offset. Maybe somebody can have a better explanation as to why it's not B, but definitely A, just because there's more products. That will always correspond. I think always is a very key word there. A student conducted an experiment to determine the rate of chemical reaction. The graph of the student's results is shown below. Which one of the following correctly shows the units of the initial rate of reaction? So here, it's basically big M over seconds to find out the rate of the reaction because we're looking at the gradient, right? So all the methods people should be pretty happy at the moment. So it'd be big M over little s. So that represents moles per liter per seconds. So therefore it'd be moles, liters, seconds. So it'd be that. Cool. Super easy question. Compared with the uncatalyzed reaction pathway, the presence of a catalyst. Um, so that's what it normally looks like. And then let's say, for example, we add a catalyst in. Okay. The enthalpy doesn't change. Okay. The enthalpy of the reactants also doesn't change. All that changes is the activation energy. Okay. Which one of the following can exist as both are? So best thing to do, I think do this one last. I'll do this one during reading time, but let's just quickly draw these out. So here, I would probably say that this is not a viable one because even if we switch these two around, it's still going to be the same. Even if we switch these two around, it's going to be the same type of molecule, right? Because these two functional groups are the same. So here it'd be so that one looks pretty interesting actually. I think that one looks good. So we've got C, um, Wait, what? Oh, wait, there's no extra carbon there. So what is that? So that's C. Okay, so that's just that. So there's no cis or trans. There's not even any double bonds there. So that's wrong, right? Here. Yeah, maybe this one looks good. So here, H, CH3, CHCl. So the reason why this couldn't appear as a cis or a trans isomer is because that's a cis isomer. And then if we switch this around, so that, that, that is a trans isomer. So they're actually different. Okay, cool. So the best way to do it is just draw these out. Let's see why this is not. So, oh yeah, so there's two CH3s, and because they're the same, even if we switch them around, there's two Cls. Even if we switch them around, it'd still be the same type of molecule. Cool. Which one of the following occurs when the end temperatures increase from 35 to 80 degrees Celsius? So because um oh, it's just a rate. So every time no matter if it's an endothermic or an exothermic reaction, the rate of the forward and the reverse reaction would both increase. That's super easy. Which one of the following they both produce greenhouse gases? Hydrogen produces water, and this would produce like CO2 and H2O. So that's true. Only petrol-powered drones produce heat. No, hydrogen fuel cell can also produce heat. They both have the same energy transformations. Petrol powered, no. So this is going through like a combustion engine and things like that. The overall reactions in hydrogen fuel cell are endothermic to exothermic. Okay. Like this is that's the reaction that's happening in the hydrogen fuel cell. And that's I mean, you can see that that's a very clear combustion reaction, which is always going to be exothermic. How many peaks will be observed? I want to draw this in structural formula. Like guys, like don't be afraid. Like even if they give you a skeletal formula, don't be like, oh damn, like this is super hard. Like just for my peace of mind, I just tend to like to draw it in structural formula, just because it's easy for me to visualize it. Okay, so that's that. And then it's connected to a carbon, which is connected to this, which is connected to that, which is connected to this, which is connected to that, which is also connected to this. Now, we can see that this carbon has a very unique sequence of bond. Okay, it's not like anything. Now, I would have said that these two carbons have the same sequence of bonds. However, there's an extra carbon there. So these are actually having their own sequence of bonds. So they're actually very unique. They're all very unique. So that's unique, that's unique, that's unique, that's unique. Now, these two, they'd be part of the same environment because this carbon is connected to this carbon, which is connected to that, and that carbon is connected to this carbon, which is connected to that. So these two is one circle, and then that's another one. Um, cool. One, two, three, four, five, six, seven. Cool. Uh, What mass? It's so the efficiency is that. So basically, we do 42 divided by 0.39 to find out how much. So basically what I'm saying is that 42 millijoules represents 39% of the efficiency, like of usable energy. So what's the overall amount of energy that we actually need to produce in the first place? So 42 divided by 0.39 is 107.69 kilojoules or millijoules, sorry. So it's millijoules. So that's the amount that we need to produce altogether. And then 19 millijoules per ton of energy is released. So then we just divide this by, oh wait, yeah, we just divide it by 19 then, which is 5.67 tons. Cool. Um, so yeah, 107, and then we divide about 19 millijoules per ton. Another way you could have thought about it is you need to think about like, okay, so I'm, I want to produce X millijoules of energy, and I know that only 39% of it is useful, so I just times it by 0.39, and that's equal to 42. So therefore, X is equal to 42 divided by 0.39. And then that gives us how much energy that we need to actually produce in the first place. Oh, I hate these questions, man. So folic acid peak area is found to be 0.35. So it's like there. Oh, man. What is that? I'd say that's smack bang. What'd you say? Oh, like, yeah, okay. I'd say approximately it'd be, yeah, 18. Okay. Is diluted to 1 liter. So it's 18 nanograms per milliliter. So in the 1 milliliter sample, so do we just, so we just times that by, so there's been a dilution factor of 1,000, right? So then we need to times this by 1,000. So what's 18 nanograms times 1,000? So for those who missed that, basically there's been a dilution factor of 1 mil to a liter, which means for, it's it means that it's heavily underestimated the amount that is actually present of folic acid, right? Because it's been diluted. So the real amount would just be that 18 nanograms times 1,000 per mil. Now, nanograms, I've never seen that before. So nanograms is 10 to the power of 9. Okay. So does that mean? So then one would be grams then, or something like that. So it's 10 to the power of 9 grams. Oh, what is that? So it's 18 times 10 to the power of 9 or something like that, grams. I think that's what it is. So if we times it by 1,000, then it'd be 18 times 10 to the power of 6, right? Because there's 3 zeros there. So then 9 goes down by 3. So it'd be 18 times 10 to the power of minus 6, which would be micro, which means it'd be this. Uh, is that right? Yeah. So it's just a bit of a unit conversion. It's actually not that bad. So yeah, 18. Yeah, so that's 10 to the power of minus 9, but then because we times it by 1,000, so it's 3 zeros, then it goes to a microgram. Omega-6 fatty acids. So don't, like, I kind of forgot this, but last time I checked, so omega-6 fatty acids, they basically have the double bond at the sixth carbon, which means that they would have less hydrogen atoms than saturated fatty acids. Saturated fatty acids have the most amount of hydrogen atoms. They undergo they undergo addition reactions more readily than saturated fatty acids. Have higher melting points? I don't think so, right? Because saturated fatty acids, obviously, they are able to pack more tightly, as I said before. Introducing a double bond into the situation will prevent the molecules from packing as tightly. So I'd say it's A. They're lower densities. Yeah, I agree. Okay. Because again, they can't pack as tightly. Water in the burette would dilute the aliquot. Always correct. Any acid-base indicator will give an accurate result. That is wrong. Water in the pipette causes an underestimate of the acid concentration. The pipette is not tapped against the conical flask. The pipette is not tapped against the conical flask. What does tapped mean? Um, Water in the burette will dilute the aliquot. Well, 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 the burette doesn't actually deliver the aliquot. Okay, the pipette does. So that would be wrong. That's wrong. The water in the pipette causes an underestimate of the acid concentration. So let's say, for example, what is it? I'm gonna quickly cheat here. Um, I just forgot what comes at the top. Is it the acid or the base? So it's a base that's there normally. I thought it could change. That's why I'm a bit confused. Let's just say, for example, we have acid and then a base here. If there's water, that means that there's less moles of base, right? Because there's water diluting it, which means that there'd be less moles of acid required to neutralize it, and therefore there could be an underestimation of the acid concentration. I don't know what that means. Um, alters the secondary structure of a protein. That is true. Hydrolyzes the primary structure of a protein. No, it doesn't. Okay, so it does not break the covalent bonds between the amino acids. It causes the irreversible change of a protein shape. Irreversible can only be caused by changes in temperature or the addition of acids. Um, no, it can be also caused by the addition of bases. So D. Methane and methanol fuel cells produce the same amount of greenhouse gases and the same number of electrons per mole of fuel. Okay, so if we go, so CH4 to CO2 and CH3OH to CO2. So if you guys can figure out the oxidation number here, so the oxidation number here, it'd be X plus 4 equals to 0. So X is equal to -4. So we're going from -4 to +4, right? Because carbon dioxide's +4. So X minus 4 equals to 0. So we're losing 8 electrons in this process. Here, it's X plus 3 minus 2 plus 1 equals to 0. So that's -2, I think. 1, 2, yep, and 2, 4. So we're losing 6 electrons. So therefore, it's a different number. And then the same amount of greenhouse gases, amount. I don't think so, because there's an extra oxygen there. So it'd be a different amount each time, right? Mm, wouldn't it be a different amount? That's the same amount. Let's quickly do it. So CH4 plus O2, CO2, 2H2O, H2O, CH4O plus O2, CO2 plus H2O. So that's a 2 there. There's a 2 there. Um, there's a 2 there. Oh, wait, maybe O2O4. Oh, maybe it changes the oxygen. Oh, there's actually the same amount. There's one carbon dioxide and two water. Sorry. It's actually big. Okay, sorry. If you guys can see in the balanced equations, there's only one carbon dioxide and two water molecules being produced each time. It's pretty interesting. The semi-structural formula is 2-methyl so it'd be this, that, and then 2-methyl there. So this is CH2. Um, maybe they're doing it from that point. So CH3. Um, so CH3 2. There's no two CHs. There's no two CH3s, right? CH2, then C, then CH3, then CH2, then CH2, and CH3. Right, so this CH2 is that. Then they've got a C, which is crowded by that CH3, that methyl group. And then we've got our CH2, CH2, CH3, and then we've got all that. Propane fuel cells is correct. Positive ions flow through the membrane to the cathode. That is true. Okay, so when C3H8O oxidizes, it produces CO2 um, 10, 18. So 18 H pluses and then 18 electrons, right? So those 18 H pluses will go towards the cathode to neutralize the cathode because the electrons are also going to the cathode and making the cathode extremely negatively charged. Voltage decreases since the reactants are used up in the half cell reactions. So that is what's different about fuel cells when compared to galvanic cells. So galvanic cells, the voltage over time decreases, right? Because the reactants are slowly getting used up. So you guys might have seen with your Xbox things, your Xbox controllers, slowly they'll start to wean off in terms of function just because they'll start to wean off in function because obviously the reactants are being used up. Whereas with the fuel cell voltages, as long as we've got a constant supply of the reactants, the voltage will kind of stay the same until there's no reactants. H2O is formed at the negative electrode, it's formed at the positive electrode. Since it is a gas, O2 is the only reactant that must have had direct contact with the electrode. That is obviously not true. Very easy MCQs. Maybe they thought that the previous years was very difficult. Which one of the following correctly describes the letter C? Okay, so when it's happening when it's at a galvanic cell, this is higher. So this is gonna go this way, and this is gonna go that way. So the the H plus ions react. So what the H plus ions are used up. Um, so the H plus ions are the reactant, right? In this reaction, right? And that's a reduction reaction, which happens at the cathode in galvanic cells. So it's either A or C. And then here we're looking at so basically I don't want to draw this all out, but I'm going to because I am confused. For more for my peace of mind. Okay, so I'm just gonna draw them as they would appear on the electrochemical series. So that's what's happening. In an electrolytic cell, these two reactants would probably be reacting, and then that would be going this way, and that would be going this way. So most likely, as you guys can see here, PbSO4 is producing HSO4 minus, and then PbSO4 is also producing HSO4 minus. So HSO4 minus ions are produced at both electrodes. Okay. So what I've basically done is I've written the equations as they would appear on the electrochemical series. And obviously, as you understand, in an electrolytic cell, you need to form a positive gradient between your two reactants. So that's a positive gradient. And then what would they be forming? They'd be forming this and this respectively. And therefore they'd both be producing um, they'd both be producing um, monohydrosulfate. I don't know. HSO4 minus ions. Viscosity, flow rate, okay. Methanol, alcohol used in, okay. So, so this is actually less viscous. So the flow rate, oh wait, no, the flow, no, sorry, it's more viscous, sorry. This is actually so this is more viscous, viscosity. This is, no. Flow rate. So then, oh, sorry, this means that's more viscous. So if its flow rate is lower, sorry. So honey would have a very low flow rate. Using potassium high alcohols used in, okay, so you use a sodium hydroxide. Why would that change? How many independent variables are there? There's two. So you're changing just because there's several biofuels. There's three, I guess, then. So there's actually your sunflower and canola oil, so that's one, your methanol and ethanol, and then your sodium hydroxide and potassium hydroxide. So there's three here. That's so weird. I mean, the entirety of chemistry you learn how this should only be one. So biodiesel made from sunflower oil. Okay. Um, have a higher viscosity than biodiesels made from canola oil. Um, no, because the flow rate here is higher than canola oil. So we can't say that for sure. From methanol, I have a low viscosity, so this is a lot. So If it has a lower viscosity, it must have a higher flow rate. So does it consistently have a higher flow rate? Yes, 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 yes. So that's pretty good. Biodiesels, um, so that is generally true. However, we can't make that conclusion from these results. Biodiesels made using sodium hydroxide catalysts have a lower viscosity. Lower viscosity, so high flow rate, no. So you can see 4.8 is lower than 4.9. So B, I'm pretty happy with. It's not letting me write. That's okay. Oh, here. So B. Galvanic cell, blah blah blah. Galvanic cell, okay. Um, so that's in one half cell. And then S2O3, SO3, and OH is in the other. So the reaction will just be 1.56 minus 0.57, which is 2 point something like that, which does not seem to be any of these things. Um, okay, so to think about this a bit more. So if we have, so obviously we have this. Now, let's say, for example, we actually had manganese. If we had manganese here, then this would be this reaction would occur. So then suddenly it would be these two that are reacting, right? Because we do have SO3 minus ions. Okay. And so I think and we already have Mn2 plus ions, and then Mn3 plus ions can just be there chilling. So if the second half cell has the manganese, then it would be 1.56 minus 1.18. What's 1.56? 2.74. What? Oh, wait, sorry. Oh, wait, oh, no, sorry, this reaction and this reaction. 1.18, sorry, minus 0.5. Okay, so it's minus 0.57 minus 1.18. Okay, what's 1.18 minus 0.57? What's 1.18? 1.18 minus 0.57. 0.61 volts. That's not it either. Okay, that's locking. Um, so at 2.5 volts, if the second half cell is manganese. So the first, okay, so we've got this. Oh, wait, what if it's this as well? No, but that wouldn't be its strongest. Mm, okay, with 1.75. Okay, let's go through these step by step. So the second half cell is just that. Then this would happen. So this reaction would go ahead. Um, and if we just have, so we have platinum, so S2O3, okay. So then this reaction would go ahead and this reaction would go ahead, which is not what we got. So it's what's 1.56 minus 0.57? 1.56 plus 0.57. It's 2.13. So these two would react if the electrode in the half cell was that. That's wrong. It's wrong. Um, if it's manganese, then the manganese would suddenly be the strongest, because it's the lowest, is it not? So it'd be that, and then it would react with the SO3 2 minus. Or unless, no, yeah, would. It'd be these two. So wouldn't it be minus 0.57? Or is there some sort of thing that I'm missing? This is a galvanic cell, is it not? Um, 1.18 minus 0.57, 0.61. I'm gonna pause the video and then I'm gonna try and figure out and then yeah. Sorry, yes, I am very, very sorry, guys. I was very tunnel vision. So I didn't realize if it was just platinum electrodes, then it'd be Mn3 plus because we don't have manganese, but it doesn't necessarily have to react with this. It'd actually react with that because it's actually a stronger reducing agent. So there should be 1.56 minus 0.94. All right. Which is 2.5 volts. So the presence of that, so there's both this and that. However, this would preferentially oxidize. That stumped me more than it should have. That was really, really stupid. Which one of the following relative molecular mass of a molecule? No, it's from the molecular ion peak, caused by the presence of different isotopes. Okay. The base peak is formed when an uncharged species is removed from the molecule. Okay. I don't think so. The height of each peak in the mass spectrum is measured relative to to the height of the base peak. Yeah, so generally speaking, that is true. So we do it relative to the most abundant ion. The peaks in the mass spectrum, they're not caused by the presence of different isotopes. I don't know. Like it's just they can be, right? But mostly it's just because of the ionization and the fragmentation of a molecule. And it should be a charged species that's removed from the molecule, right? Um, uh, so H2O2, Fe3 plus, H2O2 is here. I've got Fe2 plus. Um, okay. So then there'd be a reaction happening between this and that. Iron is deposited at the bottom of the beaker, so there is no iron sort of happening here. Yeah, there's nothing really happening with iron there. There's just like Fe3 plus and Fe2 plus. The two half reactions in the beaker immediately produce 1.09 volts. I don't well, first of all, there's no sort of voltage meter here. It's only producing heat energy. Also, it wouldn't immediately produce it, as we know. Notoriously, hydrogen peroxide has a very low reaction rate. Concentration of H2O2 decreases immediately since it is the strongest oxidizing agent. Um, wait, sorry, is it reducing agent? That is not bad, but I'm not sure about immediately. The temperature of the contents in the beaker decreases immediately when FeNO3 reacts with H2O2. It would increase immediately because it's an exothermic reaction, because obviously we're producing heat. So I'd say C. I'm not sure about immediately though, but I guess they've added a catalyst and we haven't looked. Cool. That was MCQ done. I will do the short answer very, very soon. Thanks.